The sun has been a significant area of strength for us, especially of late, and it will go through a basic, moreover fascinating change: the inversion of its enchanting field. This connection occurs generally at regular spans, meaning the midpoint of the sun power cycle, and it has broad repercussions for us here on Earth. In all honesty, the fact that the sun could rapidly present a serious gamble could cause complete interruption and fiasco for everybody in the world. The sun's allure field is made by the development of electrically charged gases in its interior, a cycle known as the sunlight-based dynamo. Over the long haul, this engaging field turns out to be progressively brilliant and reshaped due to the sun's change and convective changes. Ultimately, this cycle prompts a complete inversion of the attractive poles, where the north attractive pole changes into the south attractive pole and vice versa. So, might we at some point dissect the entire cycle and explore the sun? The sun is made primarily out of hydrogen and helium as plasma, a condition of matter where electrons are not bound to particles, resulting in a combination of free electrons and particles. The sun's inside is partitioned into several layers, with the core at the center encased by the radiative zone and the convective zone. The core is the sun's most significant region where atomic combination happens, changing over hydrogen into helium and delivering huge measures of energy. Over the core lies the radiative zone, where energy is moved outward through radiation. In this space, energy moves gradually outward as photons are absorbed and re-emitted by the solar plasma. The external layer of the sun's interior is the convective zone, where energy is shipped by convection. Hot plasma ascends toward the surface, cools, and sinks again, creating convective flows. The solar dynamo process works essentially in the convective zone and the tachocline, a thin layer that lies between the radiative zone and the convective zone. The tachocline is critical since it's where the sun's differential rotation and shear flows assume a fundamental part in making the attractive field. Now, here's something intriguing that you likely haven't heard. The sun doesn't pivot as a solid body. Rather, various pieces of the sun turn at different rates, with the equator turning quicker than the poles, a peculiarity known as differential rotation. This differential rotation stretches and winds the attractive field lines, extending the attractive field. The sunlight-based cycle is a roughly 11-year cycle during which the sun's attractive field goes through a progression of changes, culminating in an inversion of its poles. This cycle is driven by the solar dynamo and includes several phases. At the start of the sunlight-based cycle, the sun is in a state known as solar minimum, described by a low number of sunspots and negligible solar activity. The attractive field is bi and large basic and bipolar, with a distinguishable north and south attractive pole. As the cycle advances, the quantity of sunspots builds. Sunspots are locals of intense attractive movement and are related to the rise of attractive movement from the sun's inside. These sunspots show up 2 by 2 with inverse attractive polarities and relocate toward the equator over time. Around the midpoint of the sunlight-based cycle, the sun arrives at solar maximum, a time of peak activity with the best number of sunspots, solar flares, and coronal mass ejections, CMEs. The attractive field turns out to be incredibly perplexing and tangled due to the persistent winding and shearing by differential rotation and convection. As the solar maximum blurs, the attractive field begins to reconfigure itself. The reshaped and tangled attractive field lines reconnect, and the worldwide attractive field continuously switches its extremity. The north attractive pole becomes the south attractive pole and vice versa. This cycle is facilitated by the development and rebuilding of solar plasma. After the pole inversion, the sun enters the time of declining activity, returning to solar minimum. Eventually, the attractive field reconfigures, and the cycle is prepared to begin anew. Presently, we're in the solar maximum stage, and the sun's attractive field is going to flip. During this stage, we can expect to see some activity from the sun that could be as risky as it is captivating. However, the sun's attractive field inversion isn't a startling flip. Instead, it is a continuous cycle. As the sunlight-based cycle progresses, the sun's attractive field undergoes a progression of changes. At the moment, the attractive field is at its most wound and tangled state. It reaches a tipping point and begins to redesign itself, bringing about a flip. So, do we know when the sun's attractive field will flip? Researchers monitor the sun's attractive movement utilizing different instruments and procedures. Observatories equipped with strong telescopes, both on the planet and in space, provide detailed pictures of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's attractive field and its changes over time. One critical mark of an approaching attractive inversion is the behavior of sunspots during solar maximum. Sunspots show up more often and become more articulated as they push toward the sun's equator, a sign that the attractive field is turning out to be more unstable and is getting ready to flip. While we're on the subject, we should delve somewhat deeper into sunspots. When the sun's attractive field lines become turned and tangled due to differential rotation, the sun's equator turns quicker than its poles, causing the attractive lines to stretch and twist. At the point when these lines circle over the sun's surface, they stifle the convective development of sweltering plasma from the sun's inside, bringing about the cooler, hazier patches we find in sunspot pictures. Sunspots are not just intriguing solar features. They can sometimes create strong solar flares and coronal mass ejections, CMEs. These phenomena discharge immense measures of energy and charged particles into space. When directed toward Earth, they can upset satellite communications, influence power networks, and present dangers to space travelers. Increased solar activity can enhance auroras, but it can also raise radiation levels in Earth's upper atmosphere. While we're on the subject, we should inspect the distinction between solar flares and coronal mass ejections, CMEs. While both are enormous eruptions of energy from the sun, they contrast altogether. Solar flares are abrupt, intense explosions of radiation brought about by the release of attractive energy related to sunspots. They discharge a colossal amount of energy and light, often as X-rays and ultraviolet radiation. Consider them explosions of brilliant light and intensity on the sun's surface, like a huge blast. In contrast, CMEs are gigantic emissions of solar wind and attractive fields from the solar corona. They can be considered giant air pockets of gas and attractive fields being removed into space. When a coronal mass ejection happens, it sends billions of tons of solar particles into space at incredibly high rates. While solar flares and CMEs are connected, they are not the same. A solar flare can happen independently, but sometimes an especially strong solar flare can be accompanied by a CME, albeit a solar flare doesn't necessarily cause a CME. In terms of risk, solar flares can disturb radio communications, navigation signals, and represent a huge gamble to space travelers in space due to the extraordinary radiation. However, CMEs can have a more extensive effect. CMEs can cause geomagnetic storms that disturb power networks, satellite operations, and navigation frameworks. They can also enhance auroras but present serious dangers to Earth's technology and infrastructure. Another thought is that during seasons of high solar activity, the sum of high radiation arriving at Earth also increases. Satellites and other space vehicles are particularly vulnerable against raised solar movement. The charged particles from the sun can harm electronic parts, upset communication signals, and even alter satellite orbits. What else can happen to the planet? While the sun's attractive field inversion doesn't straightforwardly influence Earth's climate, the related changes in solar activity can have an impact. A few examinations propose that varieties in solar radiation can impact climatic circumstances and weather patterns. For instance, expanded solar activity can prompt a slight warming of Earth's atmosphere, possibly energizing existing climate change. Could auroras be the only positive perspective we experience here on Earth? Maybe one of the most striking impacts of expanded solar activity is the enhancement of these terrific lights. These natural light shows, known as the northern and southern lights, happen when charged particles from the sun collaborate with Earth's attractive field and atmosphere. We frequently hear about the aurora borealis, but these lights can additionally be seen around the South Pole. During seasons of high solar activity, auroras become more regular and can be noticeable at lower latitudes, offering emotional night displays. However, other than the delightful auroras, there are also additional unsettling aspects of the sun's attractive inversion that could happen if we are ill-equipped. One of the essential dangers related to an attractive field inversion is the enhanced probability of geomagnetic storms. These storms happen when solar wind, overloaded with charged particles, connects with Earth's attractive field. In extreme cases, they can cause far-reaching power outages and damage to communication systems. One such event occurred on the morning of September 1, 1859. Astronomer Richard Carrington was noticing the sun through his telescope as he had done often before. However, what he saw on this specific day would hang out in history as the first recorded solar storm. At 11:18 a.m., Carrington saw a brilliant flare of white light exuding from a gathering of sunspots. This occasion, now known as the Carrington event, marked the start of the largest geomagnetic storm ever recorded. The white light Carrington saw was a huge solar flare, an extreme explosion of radiation brought about by the release of attractive energy stored in the sun's atmosphere. This flare was so strong that it set off an enormous coronal mass ejection, CME, directed toward Earth. The CME arrived at Earth in only 17.6 hours, a strikingly brief time frame considering the sun is 93 million miles away. When the CME hit Earth's magnetosphere, it set off an incredibly impressive geomagnetic storm. The effect was fast and far-reaching, upsetting Earth's attractive field and activating currents in the ground. Moreover, transmit lines, which were the foundation of global communications at the time, experienced extreme disturbances. Sparks flew from transmit machines, operators received electric shocks, and some message stations even burst into flames. The activated currents were of such a strong extent that operators could send and receive messages even after disconnecting their batteries. One of the most striking and perceptible impacts of the Carrington event was the brilliant display of auroras. The auroras were so bright and broad that they were apparent a long way past the normal polar areas. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the sky illuminated with lively colors. The auroras were intense to such an extent that they illuminated the night sky, permitting individuals in the northeastern U.S. to read papers by their light. In the Rocky Mountains, gold excavators were allegedly stirred by the brilliance, mistaking it for dawn and beginning to prepare breakfast. Individuals described the sky as having gleaming red, green, and purple shades moving and shining across the horizon. Now, imagine if a solar storm of the size of the Carrington event were to hit Earth today. The results would be devastating. The sun is going through a gigantic change, the reversal of its attractive field, an interaction that happens generally like clockwork as part of the sunlight-based cycle. This occasion, driven by the sunlight-based dynamo, could have broad ramifications for Earth, potentially causing interruption and calamity. The sun's attractive field is produced by the development of electrically charged gases in its interior, making a complex attractive field that ultimately switches its extremity. The sun is principally made of hydrogen and helium plasma, with energy delivered by atomic combination in its core. This energy is moved outward through the radiative zone and afterward by convection in the external layers. The solar dynamo framework, which works in the convective zone and the tachocline, produces the sun's attractive field. Differential rotation of the sun, where the equator turns quicker than the poles, stretches and intensifies the attractive field lines, driving the sunlight-based cycle. At present, the sun is in the solar maximum stage, where sunspots and sunlight-based movement are at their peak, possibly causing risks like solar flares and CMEs that can disturb satellite communications, power frameworks, and present dangers to space travelers. Researchers monitor the sun's attractive action and sunspot behavior to anticipate when attractive field inversions will happen. Sunspots, which result from tangled attractive lines, can create solar flares and CMEs, both monstrous arrivals of energy that influence Earth in different ways. While solar flares emanate radiation, CMEs launch tremendous measures of solar particles into space. These phenomena can enhance auroras but also present critical dangers to Earth's technology and infrastructure. The sun's behavior is an intriguing exchange of material science and natural phenomena, influencing not just our sunlight-based framework but also life on Earth. Understanding the intricacies of sunlight-based movement is crucial, especially as we continue to depend on technology that can be influenced by solar events. The sun produces energy through nuclear fusion, changing over hydrogen into helium and delivering tremendous measures of energy in the process. This energy ventures through the various layers of the sun, eventually arriving at the surface and transmitting into space. Solar activity can manifest in many forms, including sunspots, solar flares, and coronal mass ejections. Sunspots are cooler regions on the sun's surface brought about by attractive movement, appearing as dim spots. These changes in solar activity follow an around 11-year cycle known as the solar cycle, where times of high activity, solar maximum, are trailed by calmer periods, solar minimum. During solar maximum, the quantity of sunspots increments, prompting more regular solar flares and CMEs. Solar flares are unexpected eruptions of energy that release radiation across the electromagnetic range, including X-rays and ultraviolet light. These extraordinary eruptions can influence radio communications and pose dangers to space travelers in space. CMEs, on the other hand, are colossal emissions of solar wind and attractive fields that arise from the solar corona and are released into space. When directed toward Earth, these launches can cause geomagnetic storms that disturb the planet's attractive field, prompting delightful auroras but also possible interferences to technology. The impacts of solar activity reach out past space. They impact Earth's environment and surface. Studies suggest that varieties in solar radiation can influence climate designs, possibly contributing to weather anomalies. Increased solar activity can also lead to climatic warming, which is a significant factor in discussions about climate change. Moreover, the potential for technological interruption due to solar storms can't be downplayed. A serious geomagnetic storm could harm electrical grids, disturb satellite operations, and influence navigation frameworks. Planning for such events includes monitoring solar movement and developing strategies to mitigate their effect on infrastructure. Scientists continue to concentrate on the sun's attractive field and its cycles to better anticipate when significant solar events may happen. This research involves a mix of ground-based and space-based observatories that track sunspots, measure attractive fields, and analyze solar wind. With ongoing advancements in technology, our ability to anticipate solar movement further improves, which is essential for safeguarding our technological framework and ensuring the safety of space travelers as we explore space. As we concentrate on the sun, its influence on Earth becomes increasingly clear. From the dazzling showcases of auroras to the potential challenges presented by solar storms, the sun remains a powerful force in our local planetary system. Grasping its cycles and behaviors not only advances our insight into space science, but also enhances our readiness for the effects of solar activity on modern life.